that are affected. Okay, so I want to welcome you to my lecture today. Today we are starting a new topic, an entirely new topic that we're going to do for a long time. Okay, and that was why I call this part 1. Okay, we got a lot of series of that. Okay, so we call it time series analysis. Look at that, time. Look at the word time. Okay, so the time series analysis, it's just the analysis of data sets that are collected over time. I'm going to say that again. The focus on this, our focus here is to be able to analyze and understand the set of data that are collected over time. Okay, so which means you can collect a data set or one variable over time. You can collect on more than one variable over time. Okay, so here the only independent variable we actually have to do has to be time. Okay, the independent variable is the time. Okay, so that is going to be the topic of discussion. Okay, so time series analysis. Okay, so that is what it's about. Okay, I want you to take a look at this picture right here. Can you guys see my screen right now?
Yes.
Okay, thanks for that. So you take a look at what I have in the picture right now, and this is Mississippi National River and Recreational Area. Okay, in the University of Minnesota, uh, we we got a Mississippi. Has any of you seen a Mississippi River before? For those of you who have visited the campus, is there anyone who can confirm if you have seen Mississippi River?
Yes.
Okay, thanks for that. Thanks. Okay, so what I'm trying to talk about is that we actually want to make use of this river. Okay, there's a lot of stuff to talk about. Okay, as far as this river is concerned. Okay, scientists, researchers do a lot with this river because some of them use it in their study. Okay, so but today, because this is a recreation area, and we actually collected data set based on the number of visitors that visited this area. Okay, and because we are in a world of variation, we don't expect the same number of visitors to visit in different years. Okay, if you look at, we collected data set on visitors, between 2011 and 2018. And in 2011, as you can see right here, they got 99,398. And in 2012, of course, we got 106,733, and up to 2018 that we have 417,022 people. Now, the reason why this is a time series data is because it's collected over time. Okay, now I got only if you take a look at this is just one variable that we collected over time. Okay, you can actually collect more than one variable at a time. You can collect it over time. okay? And we're going to call that a cross-sectional data, okay? When you have more than one variable, okay? I could remember when I was doing my bachelor uh, at the University of Ibadan in Nigeria. I actually work on the effects of exchange rate, inflation rate, and consumer price index on the GDP of Nigeria. Now, it means I actually, the variables involved, are more than, it's more than one, okay? The variables involved, I collected variable on GDP over time. I collected variable on exchange rate over time. I collected variable on inflation rate over time, okay? And also collected data set on consumer price index over time. Okay, so data set observations that are recorded over time are called time series, okay? Time series data, okay? So this is a time series data, okay? And you're actually going to see that the number keep changing, okay, from year to year. And it get to a point, if you look at 2014, it actually dropped, okay? And let me tell you something, there's a reason why it dropped in that 2014. We can actually trace that, okay? Because I think uh, what the manager of this recreational facility we have in mind, they actually want a situation whereby they're going to attract a lot of visitors, okay? So having a data set of this nature, the question now is, how do we analyze it, okay? How do we analyze data set that are collected over time? And that is what we're actually going to be doing in this topic. So, and that is why it is called time series analysis, okay? We're actually going to learn how to analyze data set that are collected over time. And let me also tell you, there's a reason why we are collecting this data set. And the major reason is just to be able to explain, to be able to dictate a trend, okay? We actually want to see whether there's going to be an increasing in the number of visitors to this Mississippi River. And we also want to see whether there's a decrease in the number, okay? And why do you think the manager is interested in figuring that out? I think he's interested in doing that because he actually want to know if the visitors are going to be increasing, and if the visitors are going to be increasing, then the manager need to put some measures in place to be able to accommodate a good number of people, whether they of expanding or not, okay? And if it is going down, I think they want to know the reason why it's going down, okay? So looking at at your data set over the year, they actually mention the directional movement, okay? They can actually figure out the directional movement, whether it's actually going to be increasing or it's going to be decreasing. And whether it's going to be decreasing or increasing, it depends on certain reasons, okay? Which they cannot actually figure out, okay? So that is the purpose. And you know what? If they have the understanding of the movement of this variable over time, and that will enable them to forecast, that will enable them to have a scientific prediction of the future, okay? So that they'll be able to know the number of customers on average that are likely to visit the recreation facility in the future. And that is the reason why they are trying to analyze what they have right now. So in time series analysis, we use the variation, okay, of the past to explain variation in the future. That's exactly what we want to do, okay? And you know what? As human beings, we are very curious. We got a high curiosity, about the future. Oh, what is going to happen next? We don't know. Can we have a way to predict what is going to happen next? If, based on the information that we have right now, okay? So in time series analysis, the knowledge of the past and the present can actually be combined, to predict the future, okay? Because we are always curious about what is going to happen in the future. Okay, so if I want to measure the trend, what I can actually do, I can plot this particular data set over time, okay? As you can see, looking at this trend, you're actually going to see an upward trend, right? Okay, so this is more or less an upward trend. And what I have right here is actually what we call time plots. Okay, so a time plot is actually a diagrammatical plotting of the time series of variable, over time. Okay, you can see starting from 2011 to 2018. Okay, we actually plotted the number of recreational visitors to the Mississippi National River. Okay, to the Mississippi National River. Okay, so we got a Mississippi River in the in the University of Minnesota. Okay, but the one I'm talking about here is a Mississippi National River. Okay, and recreation area. Okay, now uh, we actually, if we want to model data set, what we normally want to do is to use a what I'm going to have in a model. I'm actually going to play with notation. Okay, so because of that, I'm actually going to call the first data point to be y1. I'm going to call the second data point to be y2, and I'm going to up to the the last data point. Okay, so, and that is the essence of this. Okay, the y1 is just going to tell you, okay, that's going to be the first observation. Okay, so which correspond to 2011. So, and you know what? And that is the reason why I define time series as a sequence of data that measure the same thing over an ordered period of time. I want you to look at the word, I want you to look at the same thing. The same thing here is basically talking about the visitors. Okay, we're interested in the recreation visitors right here. Okay, so that is the same thing that we're talking about. Okay, but over, you know an ordered period of time. Okay, from 2011 2012, these are ordered. Okay, these are ordered. Okay, if you take a look at what is it called, when you want to talk about time series, okay, the time component of that actually need to be ordered. Okay, so what we are trying to say, okay, this is the way it occur in that sequence. Okay, and that is why we call it a sequence of data. Okay, can you guys hear me?
Yes.
Okay, thank you so much. I just want to confirm if you guys are hearing me clearly. Okay, so like I said, the time component, we're actually going to use t. Okay, a lowercase t here is actually going to be a symbolic representation of the time index. Okay, of the other time index. Okay, so as far as this course is concerned, you're going to see us using t. okay, as the index. Okay, and you know what? We're actually going to be using YT, the YT as that particular data point collected over time. Okay, and you know what I'm trying to talk about here is like T equal to 1. Okay, T equal to 1. So YT, this is the symbolic representation, okay, of that figure. So T equal to 1. So this is saying, okay, at T equal to 1, and what is my time 1? Okay, my time 1 is 2011. Okay, T equal to 2 is actually going to be 2012. So which means if I want to write a T, I'm actually going to write 1, 2, 3, 4, 5, 6, 7, 8, and so on like that. Okay, so that is exactly what I'm talking about right here. Okay, and this is a way that we write a time series data. Okay, a time series data, if you want to write it, you need to write YT. Okay, so that's a Y subscript T. Okay, so where T is the order time index. Okay, so a quick reminder of what you did. Let me say, remember what we did on linear regression. Okay, in linear regression, particularly in a simple linear regression, we actually look at the effect of one predictor on response. Okay, but I want to tell you this: in linear regression, the source crate 1 to n are indices used for hiding purpose. I think you know that. So in linear regression, where you have maybe the y1, y2 up to y whatever, depending, I'm talking about the response variable, depending on the number of observation you have, those are not time series, they are not collected over time, okay? So they don't necessarily mean the order of the observation, okay? But for time series, okay, we are actually referring to order. You get it now? And that was why I said, however, in a time series, Y1 always precede Y2, okay? Y1 always precede Y2 means, you know, 2011 will actually come before 2012. So which means 2011 will actually precede 2012 and 2012 will succeed 2011. And that's what we're trying to say. Okay, so the Y2 right here actually, succeed Y1, and Y1 actually precede. That's exactly what we're talking about. Okay, so in time series analysis, ordering is very, very important. Okay, because naturally time are ordered. Okay, uh, the topics, there are two concepts that we're actually going to be focusing on in time series analysis. And number one is what we call autocorrelation. Some of you remember the other time when we are working on linear regression, I told you there are absorptions, right? Number one absorption in linear regression, if you can remember what we did linearity absorption. We did normality absorption, we did the absorptions of constant variance, but there was one absorption that we have not investigated. And that absorption is absorptions of independence. Some of you have actually been reaching out to me on how you can actually investigate the absorption of independence. Okay? But let me tell you this. Every other thing that we've done before, okay, all the tests that we've done before, there is none of them, even including the plots, that will enable you to test for independence. Only that we get an you know if they are not time series data, okay, if the data we are using are not time series data, independence is not going to be an issue because if the other three assumptions are met, okay, if they hold, automatically independence actually going to hold. Because if you look at the way you collect your data set, we have an assumption in the collection of data set that from one observation to the other have to be independent. Okay, so if you set that assumption from the beginning, there is no need again, testing for independence. But you know what? When you are working with time series data, when you are working with time series data, every time series data actually have a problem of independence. Okay, and that is what we call autocorrelation. Okay, so and that is going to be one of the concepts that that I'm actually going to walk you through in time series analysis. Okay, we call it autocorrelation. The second concept that we also talk about is weak stationarity. Okay, or let me just say stationarity in general. Okay, I'm actually going to walk you through that as well as this topic is concerned. Then let me also tell you there is something that we call a white noise model. Okay, because the simplest time series model, you remember the other time when I was walking you through linear regression model, you remember we consider the simplest model with complicated models, right? And the simplest model ever in linear regression is when you talk about the intercept model, because the intercept model does not have any predictor. Okay, so also in time series, we are actually going to be talking about a simplest time series model that we actually call a white noise. Why do we call it a white noise? You're actually going to know as time goes on. Okay, just to tell you, that is one of the topics that we're actually going to be talking about. Okay, I'm actually going to walk you through them one, one at a time, and I'm actually going to have a way to relate them to what happened in real life. Okay, so you're actually going to see. Okay, and let me tell you, for those of you that are into financial, maybe financial research, or you are into financial stuff, maybe you deal with, maybe you are into banking, you are into finance, you know, you are into something that has to do with time. Okay, do you know that the COVID cases, the COVID-19 cases, we can actually look at the trend over time, because the number of cases of COVID-19 are actually recorded over time. That is the reason why if you go to worldometer, or you can actually track the number of positive cases of COVID-19, for each state in the United States of America, and you can also see, across countries in the world. And you know what? For a particular country, for a particular state, and for the world in general, you can actually see the trend of that over time. Okay, so we can measure the time, because this actually happens, you got a different number of cases of COVID in different time. And of course, what we actually want in the world now is for that thing to go down. Okay, that's exactly what we're looking for. Okay, so right now it's actually going up. So with the knowledge of time series analysis, we will be able to investigate the directional movement of the cases of COVID-19. And not only that, we'll be able to measure the number of deaths, the number of people recovered over time, and stuff like that. Okay, and that can actually, so that's a time series data set that can actually be analyzed. Okay, so there is something that I want to talk about right now. I want to start with the autocorrelation. Okay, so autocorrelation is one of the important topic in time series. And what do we mean by, of course, when I say correlation, of course, correlation is just, we're just trying to say relationship exists between two variables, okay? But you know what? Uh, the autocorrelation that we are actually talking about right here, we want to look at the correlation between YT and the lag. This is a lag of, there's a difference between, this is like a current time, the current data, okay? Okay, maybe this is a data for, if YT is a data for 2012, okay, this guy is going to be the data for 2011. Okay, so this is a I will lag this by one. Okay, we lag this one by one. At time we could have YT minus 2. That's a that means the number of lag is 2. Okay, but right now we actually, we got a YT. So let me just tell you this: the YT here is all of this. Okay, then we can actually complete the lag of that. Okay, by one. Okay, so if I want to, lag that, then the second set of variable that I'm actually going to have, we actually start from Y2 to Y8. It's not going to start from Y1. Okay, so stuff like that. So we want to look at the correlation between the current value of that and the lag. Okay, and when we plot that, okay, when we plot the YT on the vertical axis and we plot the lag of that on the horizontal, okay, we plot that because we actually want to have measure relationship between them. Okay, so and if there are relationship between them, then of course that is the autocorrelation that we actually want to talk about. Okay, now this is after plotting the YT against the lag of that. Let me now there's a way you can actually get. I'm going to show you how you're going to get this. Okay, so we got a YT now. This is like our YT. Okay, so I just need to write the lag of this. Then when I write the lag of that, I need to indicate the number of lag. If the number of lag equal to 1, okay, it's actually going to generate a data set within this one for me. Okay, that's going to be YT minus 1, okay? And that's exactly what I'm plotting that against the other one. And that is what we can see right now. Okay, so if you take a look at we're just trying to talk about a particular point, okay? So this is like the Y6 and Y7. Okay, this is, and you know what, the Wi-Fi, if you look at the Wi-Fi here, is 127.635, okay, and the Y6 is that, okay. So we're just trying to show the coordinate, okay, of each of what we plotted. That's all. That's what we're trying to do, okay. So you can see that now. So in the plotting of YT against YT minus 1, so that will give you an opportunity to, to plot the Y6 against Y7, Y7 against Y8, Y5 against Y6, Y4 against Y5, Y1 against Y2. It's like plotting, it will give you opportunity to be able to plot, you know, uh, the number of visitors in 2011 against the number of visitors in 2012. Okay, so you got a Y1 against a Y2 here, and so like that. So that is the opportunity. Okay, so we don't really. So what we're doing right here is a autocorrelation plot that I'm actually talking about. Now, uh, if I now find a correlation, okay, between the YT and the YT minus 1 that we just did right here, this is more or less like a scatter plot. Okay, this is more or less like a scatter plot. Okay, like I said, I'm actually going to give you a coding out on how to get a YT minus 1. Okay, what you have right here now is is YT. Okay, you're going to have another set of variables that's going to be YT minus 1, but the YT minus 1 is actually from here. Okay, so now the correlation here is 0.65. Okay. You remember the other time that correlation, okay, tell us two things. The correlation tell us the direction and the strength. Okay. With the correlation, I will be able to know the direction of the relationship between the YT and the lag of that. And I'm also going to know the strength of that relationship. Okay. So right here, looking at the direction is positive because I get a positive sign. And looking at the strength, okay, you're actually going to look at the strength, the closeness of the correlation to 1 will actually determine the strength of that correlation, or whether you're going to have a weak one or you're going to have a strong one, and so on like that. Okay, so what we have done here right now is just to be able to find the correlation between the YT and the lag of that. But the lag that we consider here is lag 1. Okay, do you know that we can also find a correlation between the lag 1 and lag 2? Okay, we can find correlation between lag 1 and the lag 2. Okay, we got a code in now where we can actually write, if I want to get the lag 1 and the lag 2, I'm actually going to get that from YT. I'm actually going to get that from this data set. Okay, so all what I just need to do is just to write a lag uh into the data set, and and put 1 or 2. Okay, so we can also, what I'm trying to say is that we can also find a correlation between that. So the estimated autocorrelation at lag 1, okay, and that's exactly what we just did. Okay, the estimated autocorrelation at lag 1. Okay, so now I told you the other time that the same way that we can do like we can link YT with YT minus 1. Okay, and let me just tell you, the idea is just that, okay, can I find relationship with current and the immediate past? So this is the current value of that, and this is the immediate past. Okay, it's just like, can I have relationship between the number of visitors, you know, uh, between 2000, considering 2011 and 2012, or 2013 and 2012, 2014 and 13, and so on like that. But do you know that we can also have a situation where we may not want to talk about immediate past. Maybe we want to talk about past, like 2013 and 2011, or 2014 and 2012, or 2015 and 2013. If I really want to do that, I'm actually going to lag by 2. Take a look at what I have right here. This is the current, and this is the by 2. Okay, like, looking at the relationship between the current value of the time series data, the current value of that, and the past, not immediate past. Okay, the past, not immediate past. And that's exactly what we're trying to do right here. And let me tell you something. In time series, we normally go with retrospective. What do we mean by retrospective? Okay, trying to use the idea of the past, okay, to be able to explain the current, and the combination of the idea of the past and the current. We will be able to use that to make a forecast into the future, because what we actually have inside, what we have in mind, is a projection for the future. Okay, is a projection for the future. Okay, uh, one former American president that I really respect a lot uh, uh, said, and I quote, he said, we can, I think the name of that American president was J.F. Kennedy. He said, and I quote, he said, we cannot correct the past, but we can run perfectly the future through the mistake of today. I'm going to say that again. According to J.F. Kennedy, the former American president, he said, and I quote, "We cannot correct the past, but we can run perfectly the future through the mistake of today." Okay? It means, the past has already gone. The past has already gone. But you know what? Do you know that maybe we're making mistake right now, but we believe we don't want to make the same mistake tomorrow, but we believe that the past that has gone, we can actually use the knowledge of this past with, combine with what we're doing right now, we can actually, run perfectly the future. I think I agree with JF Kennedy. We cannot correct the past, but we can run perfectly the future through the mistake of today. I'm actually going to write. I'm going to share my whiteboard because I like that quote a lot. Uh, so I'm going to write that right now for you to be able to see. Okay. Can you guys see my whiteboard now?
Yes.
Yes.
Okay. So it said we cannot correct the past. Okay, but we can run perfectly. We can run perfectly the future. We can run perfectly the future through through the mistakes, through the mistakes of today. Okay, so this is according to former American president. Okay, so and it's attributed to JF Kennedy. We cannot correct the past, but we can run perfectly the future through the mistakes of today. And that's exactly what we want to do in time series. What we want to do in time series, we want to use the variation in the past and what is happening right now to determine, what is likely to happen in the future. Okay? When you take a look at what happened in the stock market right now, of course, is volatile. Okay, there's a lot of volatility. Okay, and you know, going by the current happenings of going by the coronavirus situation and some other issues. Okay, so how can we learn from the situation? Okay, how can we actually, correct the past, you know, and run perfectly the future through the mistakes of today? We actually do. So what I'm trying to tell you is that there's a connection. We're trying to look at the connection between the current variable and the current value of the variable and past. Okay, not immediate past. And that is what we actually plotted right here. Okay, can you guys see what I'm projecting right now? The plot of yt against yt minus 2. Can you see that?
Yes.
Okay, thanks for that. Okay, so like I said, what I'm using here is a Google stock price. Okay, I'm using a Google stock price, and I'm actually using the price of today versus the day before yesterday. Of course, the day before yesterday is what I call past. Okay, and that is why the day. So if it were to be yesterday, this guy here is going to be yt minus 1. Okay, and you know what? That is what we are trying. We want to look at the correlation. We want to see whether there's a correlation between. We want to see whether there's a connection between what happened uh, today. Today is Thursday. So is there a connection between what happened on Thursday and what happened on Tuesday? That's exactly what we're trying to do right here. Okay, and we're actually using the Google stock price. Okay, And you know what? The correlation that we got is 0.912. And this is going to this is suggesting a very strong positive correlation between what happened today in the Google stock price. Okay, because this is Google, this is like the Google stock price for today against the Google stock price of the day before. Okay, and we realize that there's a strong connection in the price, okay, between what happened today and the day before. So this is estimated autocorrelation at lag 2, okay? So you can see that's what we call lag, okay? Your lagging is like going backward, okay? Going backward twice, okay? So now, before I go to weak stationarity, is there anyone who wants to ask question or who need clarification on how to figure out autocorrelation between the current variable and the lag of the variable? Is there anyone? Okay, so silence implies that you guys are good. Now, another important concept that we also want to talk about is stationarity. What do I mean by stationarity? Of course, when something is stationary, it means there is no change over time. It means we're actually going to be recording the same thing. It means that the price is not going to change. The price on Monday is actually going to be the price on Tuesday, it's going to be the price on Wednesday, and so on like that. That is stationarity. Or the number of patients, right now that we're in the middle of pandemic, when we talk about stationarity, we're trying to say the rate of hospitalization, the number of hospitalization today is the same with the number of hospitalization tomorrow, and so on like that. That's what we mean by stationarity. Okay, that is a stationarity is looking more or less like a stability. So and that's why we say the mean is constant. Okay, the mean is constant means the expectation of the y1 equal to y2 up to the last data set. So what we're trying to say in essence is that the number, like looking at the Mississippi River that I talked about the other time, it means on average the number of visitors that will come in every year is going to be the same. That's what we mean by stationarity. Okay, so by stationarity, what we mean is that on average, okay, on average, they're going to be the same. But let me tell you something, when they are the same on average, there is nothing to worry about. Okay, when they are the same on average, there is nothing to worry about. Okay, now the variance has to be constant. The variance of the time series variable y1 has to be equal to the the variance of a time variable y2, and so on like that. Okay, so when I talk about stationarity, I'm actually talking about having a constant mean over time and having a constant variance over time. But let me tell you this. Autocorrelation that I talk about the other time depend on the difference of movements. And I'm actually going to walk you through what I mean by the difference of movements. Okay, if you take a look at the first one here for lag 1, for lag 1, I'm actually talking about, it's going to be one lag distance apart. Okay, between the looking at the correlation between the y1 and the y2, it's just like looking at the correlation between what happened now and yesterday. Okay, that depends. If the unit of measurement is days, because in time series analysis, the unit of measurement could be days, it could be months, it could be week, it could be years. I'm going to say that again. In time series analysis, The unit of measurement could be days, okay? It could be week, okay? It could be month, okay? It could be quarter, and it could be year, okay? So now, what I'm just trying to tell you here for lag one, for lag one, it's just like, okay, I'm seeking for the correlation between two time series variable that are one lag apart, okay? And let me tell you something. The correlation between Y1 and Y2 is the same thing as the correlation between Y2 and Y3. It's the same thing as the correlation between Y3 and Y4, and up to the last one. This is the second to the last, and this is the last one. So to tell you that the correlation between two time series variable that are one lag apart. So is that, so this is a symbolic representation. So anytime you see this, a row into one. So row into one actually means we are interested in a correlation between the current and the immediate past. Okay, and that is the general formula for that. Okay, this is the immediate past, and this is the current. Can we look at the correlation between them? Okay, so looking at the correlation between, okay, the price, the Google stock price on Monday. Okay, is it this? Does it have a correlation with the, the price on Tuesday? Okay, so that's exactly what we're talking about. Okay, so for lag 2, it means I'm actually going to be seeking for the correlation between two time series variable that are two lag apart. Look at that, Y1 and Y3, that is two lag apart, 2 and 4, okay, 3 and 5, okay, 4 and 6, and so on like that. Then we're going to use a row, 2 to denote that. So, so that for lag K, because at times we may want to look at the relationship between the current time, and what happened, we're going to go so many far in the past. Okay, so, and that was why I said for lag K, so the correlation between the Y1 and Y1 plus K, if you take a look at the distance between this and this is going to be K. How am I going to know? You can do K plus 1 minus 1. So K plus 1 minus 1 is actually going to be K. Okay? So if you take a look at this, so for lag K, sorry, this should be a mistake, okay? It shouldn't be 3, okay? It should be K, okay? So this is supposed to be K. Okay, so because for 3, I'm supposed to have the correlation between Y1 and Y4, okay, the Y2 and Y5 and so on like that, okay. Now, and let me tell you this. I'm going to tell you why this is, you're right. I think the reason why this is 3, because any correlation that is going beyond lag 2 from lag 3 and above, from lag 3 and above, it's always going to be the same as row 3. Okay, I'm going to say that again. For instance, if I want to know the correlation between Y1 and Y3, Y1 and Y4, what is the distance? The distance is 3, right? It's going to be row 3. Okay, and if I also want to find the correlation between Y1 and Y10, Y1 and Y10, it's still going to be, I'm still going to use this to represent that. Okay, now the next thing I want to talk about now is identify non-stationarity from observed time series. Okay, if you have a time series data set, excuse me, what we want to do, since we know the definition of stationarity, that is when there is no change in mean and variance over time. Okay, no change in mean and variance over time. Now, when we have a set of time series data set, is there a way that we can actually identify non-stationarity? Of course, you know what I mean by non-stationarity. Non-stationarity is actually going to say, okay, the mean are not the same and the variance are not the same. Okay, that is going to be non-stationarity. okay? But for stationarity, of course, you know what stationarity mean. No changes in mean, no changes in variance. Okay, so if you take a look at what I have, this is a time plot, okay? You know, I plotted y against time, okay? Plotting y against time, this is a time plot, and you can see this is characterized by ups and down, okay? Can you see that now? So this is characterized by ups and down, okay? And you know what? The non-stationarity, we actually be talking about, I got a different mean, okay? And you know, and I actually get a different variance, okay? You know, non-stationarity does not really implies, I mean, sorry, stationarity, let me go back here. Stationarity does not mean I got the actual same value for different time component. You know, I got it. It doesn't say that, you know, I'm actually going to have the same values probably for Monday, for Tuesday, for Wednesday, but it's trying to say on average. There's a difference between average and the actual score. Of course, if you take a look at what I have here the other time, you can see what I have here is not, it's just the actual score. Of course, looking at the actual score, okay, they're going to be different, okay? But what stationarity is talking about on average, okay? You know, the average of that has to be the same or true, and the variance of that have to be the same or true. That's exactly what we're talking about here. We're not actually saying that, you know, the actual score are going to be the same. But what we're trying to say, what is going to be the same is, okay, the mean and the variances, okay? That's exactly what we're trying to say. Now, if you take a look at this data point, if you take a look at this time plot, we can actually identify non-stationarity. Okay, and what do we mean by non-stationarity? The non-stationarity is actually going to tell us that, okay, we're actually going to get a different mean, okay, and that is what it's going to tell us, and the different variances, okay. Now, and if you take a look at what I have on this time plot right now, you're actually going to see that it's actually show that the variance is not constant for all t. Okay, look at the way it is dispersed right here. Look at the way it is dispersed right here, and look at the way it is dispersed. So at different values of t, you know, there is you know, the way the data set is being dispersed, okay, it varies. Okay, so and that was why we said that the variance seem to increase as t increases. Okay, the variance seem to increase, and take a look at that. What we have right here is different from what we have right here, and it's different from the expression here, and so on like that. Take a look at that. Okay, so looking at a time plot, we will be able to see whether there's a change in variance over time, okay, and the change in mean, okay. And when there is a change in variance over time, or there's a change in mean over time, then we're going to say the time series is not stationary. Okay, it is not stationary, it means it is non-stationary. That's what we mean by non-stationarity. Okay, and you know what? In a situation where we got something like this, it's more or less, it's looking like an absorption violation that we did in linear regression. Okay, because time series model actually have assumptions of stationarity. Okay, there is assumptions of stationarity. Okay, and we got a way to test, we got a way to investigate whether this stationarity assumption is violated or not. Okay, and the stationarity assumption will actually be violated if you look at the variance over time. If the variance keep changing, just like the data set that we have right here, if the variance keep changing over time, then we're actually going to say the time series is not stationary. Okay, so we want to look at another one. If you take a look at this, of course, if you compare what I have right here, if you compare to this, look at the expression right here. And the expression right here, you're actually going to see that these two set of variables are not the same, okay, in terms of the expression over time. Okay, if you take a look at what I have right here, we're actually going to see that this is stationary. Okay, it is stationary because the mean, if you take a look at what I have here, okay, let me see very well. Oh, the variance look the same, but if you look at the mean is changing. Okay, let me take you back. If you take a look at what I have here, okay, you're actually going to see that what is changing is the variance. Okay, and if I want to take a decision on stationarity, okay, it's either, if I take you back, okay, these two, if there's any violation of any of this, then there's a stationarity, there's a non-stationarity problem. I'm going to say that again. It's either if because for you to record the stationarity, both the mean and variance have to be constant. In a situation where the mean is constant and the variance is not constant, there's a problem of non-stationarity. Okay, and that was why if you take a look at what I have right here, and the variance was not constant, okay, and that is the reason why we said the time series is not stationary, even if the mean is constant. Okay, because there's a difference between if a mean is constant and when a variance is constant. Okay, so but if you take a look at what I have here, you can actually see that the mean, if you take a look at this, despite the fact that maybe the variance of the data set may more or less kind of stable, but the mean does not appear to be stable because it is just going all the way up. Look at that. The mean is actually going all the way up. So this is more or less showing a positive, an upward movement. I'm actually going to call that an upward movement, okay? Because the mean appears to go up when t increases. And let me tell you this. This is basically what is happening, in some states in the United States right now, and in some countries in the world, as far as COVID-19 is concerned, where it is actually going up. Okay, so the essence of that, it means it is not stationary. Okay, so that was why we conclude that the time series is not stationary. Okay, it is not stationary because the mean is not constant over time. Okay, so if you look at the time series too, and that is the only thing, uh, that is why it fails a stationarity test. What we're trying to do is just like we got two set of variables that are time series, that are collected over time, and we actually uh, want to test them for stationarity. Okay, but what we're doing right now, this is not a standard statistical procedure to figure out the test. I'm still going to walk you through the standard, because there could be a conflict in the way some of us will read the graph, and that's why there's still going to be a kind of a standard technique, to test for stationarity. But what I'm just trying to show you right now is just like, okay, we got two variables, and we're trying to investigate each of the variable that are collected over time for stationarity. Okay, and of course, I show you right here, the variance appears not to be the same, and because of that, we conclude that this time series variable is actually not stationary. And here, because the mean is actually going up, but the variance is kind of very close to stable, but the mean is actually going up. Because of that, we conclude that that is not stationary. I think I get something on my chart. Let me see if the person is somebody said, can the mean and variance be non-constant on a subset of time? Of course, it depends on the nature of data set. Okay, it depends on the nature of data set. We can have a situation where the variance are changing and the mean are also changing in the same data set. It's possible. Okay, and let me tell you something. As time goes on, for those of you that will go further in, that will take an upper level course in statistics, you actually see going to hear something about what we call a change point. Okay, you're still going to hear what we call a change point. Okay, and in the analysis of change points, what we normally want to do is just to see whether there's a change in mean and a change in, not only change in mean, also change in variances. Okay, but let me tell you something: the fact that we could have a change in mean may not imply a change in variance, and change in variance may not imply a change in mean. And we can also have the two at the same time in a particular data set. And that is the reason why we actually need to investigate. Okay. Okay, so sometimes the time series plot will mislead us, just like what I told you. Okay. So what we're doing right here, you know, they are not a standard way to do that because there could be conflict of interest in a way we interpret the graph. So sometimes the time plot will mislead you, will mislead you. For example, the following time series is stationary according to its population model. However, the time series plot suggests an increase mean. What is going on? Okay, and that is the reason why at times we could have a conflict between what what the time series plot is going to tell us, okay, and what we actually going to see in the population model. Now, can you guys see my equation right now?
Yes.
Okay, so when you look at the equation that I have right here, this is more or less, looking at the relationship between the current value of the series and, the immediate past. Okay, so this is like one that we talk about. Okay, and you know what? The WT here is the error. We also going to call that a white noise. Okay, so and you know what? The contribution of the immediate past to the current past is the 0.9. I'm going to say that again. The contribution of the current of the immediate past to the current past is just like uh uh maybe the price of a stock today. Okay, let me tell you something. The effects of the past will also be felt. Okay, because we realize that you know uh a shock in a particular period could actually be felt in another period. Okay, it's just like the mistake of yesterday, okay, can actually be felt today. Okay, how does immediate past, explain what we are facing right now? We know that 2 days are not going to be the same in business in anything. We know 2 months are not going to be the same. 2 days are not going to be the same. 2 weeks are not going to be the same. But the question is, what is the contribution of yesterday to today? Okay, so take a look at what I have here. The 0.9 is actually saying that, you know, yesterday, okay, the immediate past actually have a connection. Okay, it has a connection with what is happening now. And this is so strong because you know what? The value that I'm actually going to have here, we go from 0 to 1. Okay, the moment it is 0, then there is no connection between the current and the immediate past. Okay, but the moment it is very strong like this, then there's a strong connection. Okay, so that is what this model is actually telling us right now. Okay, so we're going to assume that the WT, you remember what we did before, be looking at what I have here as more or less like, okay, the two that I have here is going to be the beta naught. This is going to be acting like a beta one, but we get a name for that in time series. We're going to call this rho. This is a correlation that I talked about the other time, okay? And you know what? This guy here is more or less as a stochastic component of the model, okay? And you know what, like the error time, okay, and it's actually going to follow a normal distribution with mean 0. And you know what, this is going to be the variance of that. Okay, so this is the variance. We are specifying that for this model. Okay, so if you look at what I have right now, In a situation where we got 50 of observation, okay, and we actually want to make a plot, okay, of YT, okay, we want to make a plot of YT over 50 observation, okay, and that's exactly what we have right here, okay, and you can see that this is just like, okay, I'm plotting YT, but you know what, my YT, this is my model. It's just like, okay, I want to plot this YT, okay, against time, okay, and that's exactly, look at the shape right here, okay, this is like going up, okay, can you see that now? Now, if we have 50 observation, okay, now let's see what happened if we collect more than 50 observation, okay. So what is going to happen if we collect more than 50 observation? Okay, when we collect 100 observation, we're going to see what happened. And when we collect 1,000 observation, we're going to see what happened, okay. If you take a look at what I have here, you know, for 100 observation, you can see what happened is going, this thing started going up and started coming down. I want to tell you this. If you look at the cases of COVID-19 in some countries at time when it started, because at the beginning of the pandemic, okay, it's expected to be increasing in an exponential rate, okay, but it's going to get to a point uh, when people are following the guidelines of by the CDC, maybe you are trying to follow the social distancing guideline, you're trying to do all the whatever guideline that that they actually put in place. Of course, you expect the curve to be kind of flat, okay, but you know what, it could be flat at some time and pick up again, okay. So, and that's exactly what is happening in some states in the United States right now, not only in the United States and in some other countries in the world, where people relax the social distancing, and the case now go up again in some states. Like, I could remember, like states like Florida, you're going to see that it has gone up again, okay. So look at that. So this is like looking at the observation over time. This is for 100, for 100 data point, okay. So but if I look at it over 1,000, over so many, it could be so many days, or there could be so many more and stuff like that, and this is exactly what I'm actually going to have, okay. Can you see that now? So what were we trying to say? So what we're trying to say is that as we increase the number of observation, we can see that the time series slowly converges to 20, and then stay at that value with small fluctuation, okay. So if you take a look at that, you're going to see that it started increasing, and it get to a point, it's just stable around 20, okay. But there's a little little bit of frustration, so it's going. But if you collect more observation, you're going to see that stability that we talk about. It's actually just going to be revolving around 20, okay. And you know what, is that is what some of the countries are actually looking for in the whole world. Like, what they're looking for now is that, okay, the cases, let us try in a way, to flatten the curve, okay. And when we flatten the curve, then of course, when you succeed in flattening the curve, it's actually going to be going down, okay. So that's exactly what we're trying to say, okay. So it's synonymous with that. So the mean and the variance seem to be constant, for t greater than 40. Okay, so if I want to look at that, when I you don't talk about constant right here, you don't talk about stationarity here, because this is going up, but you can talk about stationarity around here, because stationarity is an attribute of stability, and that actually happened. Take a look at what happened around 40. Look at that. Look at, can you see that now? Can you see what I'm pointing at right now? Can you see that?
Yeah.
Okay, so starting from 40, okay, all the way, you can see some stability. Okay, seeing stability is seeing stationarity, okay? And so we can see that the time series slowly converges to 20, okay? It converges to that point, okay, 20, and then stay at that value with small fluctuations, okay? It's not going to be a perfect straight line. There's going to be a a very small fluctuation, okay? So that's exactly what we're seeing right now, okay? So the mean, okay, the mean and the variance seem to be constant for t greater than 40, okay. So I think you can see that. So if you take a look at the, in fact, basically you can see that here, clearly than this, because this is more observation. Okay. So what we're trying to say, okay, when we are in when we are in crisis, the crisis is not going to stay for a long time. It's still going to go away. Okay, and that is the reason why I'm actually going to use this opportunity to tell every one of us that we are in, that are impacted by COVID-19 right now. It's still going to go away. We're going to come together again. We're going to be happy again. Okay, we're going to, but right now we are only staying apart, you know, to be able to stay, to come together. Okay, so that's what we're trying to do. That is a sacrifice. Okay, because it's not easy to, you know, to be in isolation. It's not easy at all. We need one another. Okay, so the increasing trend we see at the beginning is due to an unfortunate starting point. Okay, the y1 equal to 0. We are actually starting from that. Can you see that point now? So it takes about 40 time period for the time series to climb out of that valley. Look at that. So, and that is exactly what we're trying to, what some countries are trying to figure out right now. Something that started increasing. How many days or how many months are we actually, are things likely get, need to get back to normal? Okay, before things can get to normal, we need to first, you know how many times the period is going to take us to get to the peak. Okay, when you get to the peak, then you're actually going to be stabilized, then it's going to be coming down, and just like what the New York is doing right now. Okay, you can see that before in the beginning of this epidemic, the state of the New York has the highest cases of COVID-19. Okay, the rate of hospitalization day by day, as at that time, was so high. The number of deaths was so high. The number of cases was actually very high. But if you look at what is happening now in the New York, I think some of the states in the United States have already reached their peak. Okay. So, and the question is, how many days, how many months, will take us to get to that peak? Okay. And just like based on what you see on the data set right here, it actually take about 40 time period. Okay, if you take a look at that, before we started experiencing that stability. Okay, it's not going to be a total stability, it's not going to be a total stationarity. There's going to be some little frustration. Okay, and that's exactly what we are trying to see right now, and that's what we are trying to see right now. Okay. um Therefore, even though YT is stationary, the first part of the plot misled us to believe that it was not stationary. Okay, so when you take a look at the first, part of the plot, it's looking as if it's actually going to be going up. Okay, things are not going to be stable. Okay, but in the end, by the time we investigate further, we realize that stationarity was still achieved. Okay, so but the question is, at what time period, how many time period are we required, to be able to attain stationarity? Okay, so we want to look at the error of the time series model right now that we call a white noise. This is what I call a white noise. Okay, in the actual sense, what do I mean by a white noise? If you take a look at this guy, you will believe that this guy is also is explaining the current value, but any other thing that we may not want to talk about in the model that can actually explain the current value of this is what we call a white noise. And you know that since we don't capture that in our model, well, we're actually going to believe that it should follow a normal distribution with mean zero. Okay, and that's exactly what I'm trying to talk about right here. Okay, the mean of that should be zero, and the variance should be this. Now, some of you may be wondering, what is the difference between what I have right here and what I have in the distribution of the error time in the linear regression model, okay, I want to tell you they are the same, okay. I want to tell you they are the same, okay. But the question remains that we still need to investigate whether we're going to have, whether the mean is actually going to be zero, okay, and we need to investigate that for the variance as well. So we want to have this an example right now where the rho, this is a rho 0.97, okay, and we are actually interested in modeling relationship between the current and the immediate path, okay. Now that is that. So if you take a look at the entire model, okay, this is the deterministic part of the model, okay. This is the deterministic part of the model, okay. And you know what? The other part is the random part of the model, okay. Just like what we have in most of the statistical models, okay. Particularly the models that we use in explaining relationship between variables in such a way that you know effect one variable can actually be determined from other variable. We always going to have a model where we're going to have a systematic part that we call the deterministic part, and we're always going to have a random part, okay. And the random part is what we call the noise, okay. And we believe the method of that we're actually going to use in estimating parameter in such model, we ensure that the random part will have to be drastically reduced, okay. And if it's drastically reduced, we're actually going to call that a noise, okay. So that's exactly what I'm trying to tell you, okay. And you know what, like I said, is similar to linear regression model, okay. When you take a look at the linear regression model, you can see what is in the rectangular box. That's a deterministic part that I also call the systematic part, and the other one is actually the error part. I think you know that. It's actually the random part, okay. So to tell you that the time series model, okay, what we have here is synonymous with what we did in the linear regression model. Okay, can you give me 1 second? Okay, thank you. Suppose YT equal to that is the model for the daily revenue from an ice cream store. Okay, suppose this is the model we're actually using, okay, as a daily revenue, okay, from an ice cream store. Okay, if you take a look at YT, the YT is the amount realized daily, okay, from the sales of ice cream, okay. It's like a revenue, okay. And you know what, we're trying to build a model where we can actually link the current amount realized with the immediate past, okay. So that is the model, okay. Now, having this as a model, okay, if you take a look at what I have is 0.97 YT minus 1 is the one that I call the deterministic part, is the one that I also call the signal. Okay, we call that the signal, okay? So this is that. And you know what? We're also going to have the noise, okay? We got a noise, okay? So that is that, which is WT, okay? And you know what? If the time component, okay, we got a 1, a 2, a 3, a 4, and so on like that, okay, that are order. Okay, the time component may be, are we talking about days, or are we talking about months, or are we talking about week, are we talking about year? Okay, if you're talking about week, this is going to be week 1, okay, the weekly revenue. But you know what, because what we're talking about here is daily, okay, daily, okay. So this is going to be in days, okay. It could be weekly, it could be yearly, but here we're talking about daily, okay. If you take a look at this, what I have here, I'm going to show you something right now. The essence of the 100 that I have right here is just that if I know the value, okay, this is a 0.97, okay, if I multiply by that, okay, that is actually what I'm actually going to have. But it's going to make sense when I'm still going to, when we are working on data set, okay, you're going to see how it's going to make sense, okay. For right now, it may not make sense to you, okay. So we're going to revisit that. So the white noise model. So let's look at the white noise model. Now, like I said, this is just a time series model, but I want to, this is a time series model because at least I have one lag, okay? It's just like a simple linear regression model where you have one predictor, okay? And you know what? When we're dealing with a simple linear regression, we also considered intercept model, right? Where we have y equal to beta naught, okay? Alone. Okay, that's what we call the intercept model, okay? But in the case of a time series, we don't talk about intercept model, but we're going to talk about the white noise model, okay? So in the white noise model, I want to show you what the white noise model look like, okay? So this is a white noise model. Okay, in a white noise model, there's going to be a combination of a constant, okay, and the white noise. Okay, the white. So what we're just trying to say right here is just that there is no connection between the daily revenue and the past daily revenue, but only that we only have connect. The only thing that can explain, the current daily revenue is a shock. Okay, this is a shock. A shock in the process. There's something in economics that we call a shock. 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 Okay, so in a situation, so what we are trying to say is that the amount that you realize daily can only be explained by chance. Okay, can only be explained by chance. Okay, it means it is random what you are getting in terms of revenue. That's what we're trying to say based on this. It means if you don't want to make use of the, if you don't want to link this with the past, if you are actually linking that with a white noise, then you are trying to say what determines what you are getting in a day is actually a white noise. And that is a random. You could get anything. That's what we're trying to say. Okay? So that is what we're trying to say. Okay, can you see that now? So, and the white noise, I told you, this is the distribution and says a constant. Okay, so now let us now focus on one thing. So the two time series below were generated using the model. Okay, so what we want to do now, we actually want to generate a time series data based on this model, based on the white noise model, okay? And we simulate the data, and I just for the purpose of explanation, okay, you're actually going to see, okay? Now, this is a simulated time series. You can see the behavior over time. And this is another one that we also simulated, okay, as you can see that. And when we are simulating that, okay, we are actually simulating that from a standardized normal distribution, okay. The standardized normal distribution between 0 and 1, it means when you simulate from that distribution, it's actually going to give you negative and positive, okay. And that's why you got negative and positive, okay, because standardized normal distribution is a combination of real number, okay. You talk about you can have values in real number, okay. You can have a negative, you can have a positive and zero and stuff like that. Okay, so based on the model that we generate, okay, we actually want to look at the autocorrelation function, autocorrelation at lag 1, autocorrelation at lag 2. We can also talk about autocorrelation at any lag that we want to talk about. Okay, so let's take a look at that one by one. We want to examine the estimated autocorrelation using the generated data, okay? Like I said, the data set that we generated, is right here, okay? And of course, we are generating from a white noise, okay? And the distribution that we actually use in that generation is a standardized normal distribution, and that is why you have a combination of a negative and a positive. So my TA is actually going to walk you through how you can do a data generation. Okay, so if you want to obtain the autocorrelation at like 1, you actually need to do need to have a plot of yt against yt minus 1. Okay, I told you before. Okay, so and then if you take a look at what I have right here, okay, you're actually going to see that the yt and yt minus 1 don't see correlated. Okay, you remember the other time when I was teaching you something on correlation, what did I talk about? Correlation, or only applies to linear relationship. But what can you see right here? This is not linear. Okay, this is not linear. Okay, and that is the reason why we said, the yt and the yt minus 1 don't seem to be correlated. Okay, and that is what you can also see in the other one. Okay, can you see that now? Okay, so I told you the other time a situation whereby the scatter plot. Okay, when the scatter plot, you know, when you have a scatter plot of two variables and you don't have linearity, okay, then it doesn't make sense finding correlation value, okay, because correlation only applies to linear relationship. Correlation does not apply to non-linear relationship. Okay, so if something have a non-linear relationship, it means something needs to be done if we want to actually find a correlation. So based on the simulated data set for the lag 1, for the lag 2, we don't see any correlation. Okay, now if you take a look at that of lag 3 as well, we don't see any correlation. Okay, so what we have done so far, we have looked at the correlation between and can somebody tell me, I want to award an extra credit right now. Okay, and this extra credit is special. Okay, and I need the person to tell me right away, why is it that there is no correlation? I investigated lag 1, for lag 2, for lag 3, there is no correlation. Can somebody tell me why? Why do we have that? Why is it that there is no correlation between what we investigated? Can somebody tell me? Somebody said it is not linear. I know. Somebody said they are independent variable. I know that they are, but I need you to tell me. Good job for saying that, but I need somebody to tell me now, okay, why is it that they are? There is something that I want you to tell me. What do you think is responsible for that? I know that because they are independent, okay, that is why they are not correlated. I know you are right, but I need you to tell me there's a reason. Okay, there's a reason why they are not. Okay, I'm going to check my chat again. Somebody said, oh, okay, let me see how I can reply to this person here. Let me see, can I reply to uh uh will you I'm sorry, I don't know, because maybe you don't want me to mention your name, but there are two people here who got it right. And I mean, if I don't mention your name, uh, okay, this is what I'm going to do. I'm going to give you the last three letters of your name. Okay, because for security reason, I don't want to mention your name. Okay, for those two people that got it right, they need to send a message to me for extra credit. And I want you to listen right now. I'm going to mention the last letters in your name. Okay, the last letters in your name. The first person that got it right, the last letters in your name is AUD. AUD. Okay? The last letters in your name is AUD. If the person get the information now, I need the person to say yes on the chat. Okay? AUD is your last three letters of your name. AUD. And the another person that got it right, okay, the last three letters of your name is ANG. ANG. Okay, the name that I'm talking about that starts with that lasts with ANG actually starts with TIA. Okay, and the other one, your name, the one that starts, okay, okay, that person have replied. Okay, I'm AUD. Okay, I need a person of ANG, you know, to also reply, so that I will be, oh, good job. Okay, so the two of you will send a message to me for extra credit. Okay, so the two of them said that the model is white noise, and the other person said because it's a random error. Of course, look at where we generate our data set from. The data set that we're using I'm going to show you now. The data set that we're using was actually generated from a noise. When you generate a data set from a noise, okay, when you generate a data set from a noise, okay, of course, you don't expect to have a correlation in the lag, okay? Any lag that you investigate, okay, because we have generated the data set from the, from the white noise, okay? So we're going to our YT equal to WT, and the WT is a white noise, okay? And that is the reason. And that is why I told you the other time, when we were dealing with the linear regression model, okay, when we don't really talk about independence, to investigate independence, because when we're collecting our data set, the observations are independent. Okay, we have assumed that observations are independent. Okay, and that is exactly what we're investigating right here. If our observation, because any observations that you simulated or you generated from the white noise, they're actually going to be, when you look, they're actually going to be independent. Okay, so, and that is why I said, looking at the revenue that I'm talking about, the daily revenue that I'm talking about, okay, looking at this that I'm talking about in a situation, okay, where this is zero, okay, where there is no correlation, okay, of course, you're going to have YT equal to WT, okay, and the YT equal to WT means the daily revenue from an ice cream store cannot be linked, okay, to any predictor. It cannot be linked to the past. Okay, it cannot be linked to the immediate past. What I'm going to generate, what I'm going to have as a revenue today, what I got yesterday cannot explain that. What I got a day before cannot explain that. That's exactly what we're trying to talk about in a situation where where the data set is from the white noise. Okay, so where the data set is from the white noise actually mean that there is no connection. Okay, between the lag, we don't talk about lag. Okay, so that's exactly what we're talking about right here. And that is why I said this is consistent with the theoretical properties of the white noise model, because the white noise model said the YT is independent of the other one. Let me also say, though, maybe the way I asked the question the other time, some people that also said independence, okay, I think I'm also going to reward them, okay. I'm going to give them half points, okay. But those who mention the data generation process, okay, those who mention the white noise or the random, okay, those two people are those that are going to have a full extra credit point. But those who mention independent, okay, those who mention independent, okay, I'm actually going to give them half point, because I've sent this to you before. Of course, you have already seen this, okay? So that actually confirms the theoretical provision of, that, okay, when I'm working with it, time series variable, they should be independent from one another, okay? So in a situation where they are independent, so independent means, the cases of COVID-19 today, is independent of the cases of COVID-19 yesterday, okay? So anything that I collected over time, okay, what we're trying to say, what I record at a particular time does not depend on either on the previous past. That's exactly what we're talking about, okay? Now, I want to talk about my sleeping pattern right now, okay? So Kazim's sleeping pattern, I want to talk about that right now. I want you to see, suppose the model for Kazim daily sleeping hours, okay, is actually white noise, okay. What is the meaning of that being a white noise? Means I can sleep at any time I want, okay. The white noise means the time I slept yesterday does not have any effect on the time I'm actually going to sleep today. That is the meaning of a white noise. Okay, so if my sleeping pattern, if my sleeping hours is a white noise, okay, so I'm actually going to have something like this. Okay, take a look at my time plot. Okay, don't forget I'm actually generating my data point, but you know what, this time around, generating my data point, I'm actually going to make use of the positive one. Okay, I'm going to make use of the positive values. Can you take a look at the positive values? Okay, because the time is positive. Okay, so now take a look at that. So for over 100 days, okay, what I'm showing you right now is my sleeping hours pattern. Okay, from here you can look at the pattern. Okay, you can look at whether there's a directional increase in the hours over time or not. Okay, you can actually see that. Okay, but you know what, I'm actually using a white noise. Okay, and using a white noise means the time I'm going to sleep today does not really depend on the time that I slept yesterday or a day before yesterday and so on like that. That's a white noise. Okay, so as you can see that now, okay, that is just to showcase a trend, okay, in the process. Okay, now when you take a look at what I have, I want to find the average of my model right now. Okay, so finding the average of my model, okay, it's actually going to be 8. It's going to be 8 because the expected value, what is the expected value of the white noise? The expected value of the white noise is 0. Okay, look at that. It's under absorption right here. Can you see that now? So it means the 8 that I'm getting here is on average. Okay, is on average. It means the daily sleeping hours. It means on average, I'm actually going to sleep for 8 hours. Okay, that is what it's trying to say. Look at that. This is corresponding to 8. Can you see that now? So I'm actually talking about, the number of hours that I sleep in a day. Okay, does that make sense to you now? That's exactly what I investigated over 100 days. Okay, so the variance. Okay, so the variance of that, this is the way I'm going to go. The variance, okay, the variance of a constant, this is a constant, is going to be 0. So I'm going to be talking about the variance of the white noise. And you know what, the variance of the white noise is equal to 1. Take a look at that, because it's 1. Okay, we have already specified the distribution right here. Okay, uh in a situation where my model is a white noise, of course, the number of hours that I sleep today will be actually will not depend on the number of hours that I slept in the previous day. So which means there's going to be independent, right? There's going to be independent in my sleeping hours, okay, in my daily sleeping hours. And if there's independent, what am I talking about? What is this? The row 1, the row 2, up to row K will be equal to 0. What do I mean by row 1? Okay, I'm actually going to take you back, to that. Okay, the correlation between lag 1, that's what we mean by row 1. The correlation between lag 2, what we mean by row 2. The correlation between lag 3, look at that. Remember when I was teaching you this one? Okay, the correlation, across, whether for lag 1, whether for lag 2, and so on like that, they actually going to be equal to 0. Of course, correlation will be equal to 0 when you are talking about independence, right? Okay, and that's exactly what I'm trying to show you right here. Okay, that the correlation at different lag will actually be equal to 0 if I generate my data set from a white noise. Okay, and that is why row 1 is going to be equal to row 2, it's going to be equal to row 3, equal to row K, and then we got to equal 0. Okay, so it means the autocorrelation at any lag K will be equal to 0. Autocorrelation, it means, there is no connection between my daily sleeping hours. Okay, when you look at my sleeping hours for Monday, it cannot be determined for my sleeping hours on Sunday. Okay, they are not related. Okay, that's exactly what I'm trying to say. So it means if I go to bed and sleep, okay, for a good number of hours, okay, that I like, okay, if I just do that erratically, then it's more or less like generating my data set from a white noise. But there are some people whose their sleeping hours, the number of hours they're going to sleep on Monday may be different from the numbers of hours they're going to sleep on Tuesday. The number of hours that they sleep on Tuesday may depend on Monday. And the numbers of hours they sleep on Wednesday may depend on the numbers of hours for Monday. It depends on the lag that we're talking about, okay? So, and that was why we said, now I'm going to ask a question. I say, is this model consistent with common sense? Okay, a situation whereby, looking at it from a common sense, does it really make sense that I said, okay, I just decide to sleep, the number of hours that I like in any of the day. Okay, so now, is there anyone? But before I go today, uh, can I ask a question from you and for whoever I want to share? This is my own daily sleeping hours. Okay, this is my model. Okay, my model is more or less like a white noise. Okay, does your own also look like a white noise, or the number of hours you sleep on Tuesday, does it depend on Monday or something like that? Does the number of hours you sleep in a particular day actually depend on the number of hours for another day? Can somebody share? Are you guys hearing me? Are you guys hearing me?
Yep.
Okay, so I need someone to share with me right now if does your whole sleeping model, sleeping out a daily sleeping hours model. Okay, people are responding. Thank you for responding. I'm going to read my chat. Somebody said, I think it does depend, because if I don't sleep a lot one day, I will sleep a lot the next day. Oh, good job. Thanks for sharing. Thanks for sharing. Somebody say, yes, it does. Like there is a dependence. High and lows are next to. Good job. Good job. Good job. So, what I'm actually asking you now is like a personal question for you, okay? Merely seeing my own sleeping, daily sleeping hour model that is stochastic in nature, okay? That is a white noise, because I can decide, you know, the number of hours that I sleep on Monday is different from the number of hours that I sleep on Tuesday, and so on like that, okay? And they don't depend on each other, okay? Now, my question to you right now is that, okay, does my model, does the whole model also look like this, or you got a different? Okay, somebody said my sleep schedule is also dependent on my sleep schedule the day before. Thank you for sharing. Okay, so let me tell you something. In the actual sense, the white noise does not make sense. In the actual sense, the white noise model, in a situation whereby I want to tell you, this is not my actual sleeping, daily sleeping hours, because the reason being that I just use this as a tip, as an hypothetical, example, okay, just for you, just for me to teach, okay. But I want to tell you, having a white noise model in a situation where the white noise determine, okay, in a situation where the white noise determine, or something, then that is not good at all. It means anything can happen, anything, you can record anything. And we don't want that kind of situation, okay? And that is the reason why I said, is this model consistent with common sense? We're talking about common sense. And that is the reason why I agree with you guys, okay? I agree with every one of you, okay? For those of you who have commented, okay? So somebody said, yes, it does. Like there's a dependence highs and lows are next to each other. Yeah, good job. And somebody said my sleep schedule is also dependent on my sleep schedule the day before. Good job. Because there are some people that may be working, and maybe they want to go to work the next day, and somebody, okay, they're going to say, okay, you know what, I think I need to sleep on time, or I need to sleep for this also number of hours because the reason being, stuff like that. Okay, so we're talking about what is real. We're talking about reality. Okay, that's exactly what we're talking about. But what I'm just trying to tell you right now, there's what we call a white noise. Okay, there's actually what we call a white noise. So this is just to explain a white noise model. Okay, so the white noise model is just basically telling us that, well, there's no way we can link what is happening now, okay, with what happened in the past. That is what the white noise is talking about. Okay, and that's why you don't see any, and you can only use this where you realize there is no connection, there is no relationship. Okay, the two variables, the two time series variable are independent. Okay, and that is the reason why you can only have a white noise model. Okay, I'm going to say that again. Okay, a white noise model. Okay, having a white noise model, of course, the correlation of with respect to any lag is going to be zero across board. Okay, and then they're going to be independent. Okay, so which means there is no connection between what we record now, okay, and what we record in the previous past. Okay, it could be immediate past, it could be a past, and so on like that. Okay, so I want to thank everyone for attending my lecture today, and I hope you guys really enjoy that. Uh, until tomorrow, oh sorry, until Monday again, then I'm actually going to come your way with another exciting topic. Though we are still going to be working on time series. Okay, I want you to make sure you have make sure you stay safe, and do have a good day. Uh, I think somebody has a question. He said, will you post any specific instruction or guides for practical assignment 2? And I think I've already done that. I need you to check the module that have been done, check the announcement section that have been done. What I only want from you in part 2 is to submit your data set. That's all. Part 2, submission of your data set. Okay, there's nothing to do again. Okay, just submit your data set for part 2 in the practical 2 part. But for part 3, then you follow the instruction that I've already attached. You can check the announcement section, or you can check the module. You're actually going to see the instruction where you are actually going to follow from introduction to the reference. Okay, so I think I need you to follow that project format. Okay, so I'm going to repeat that again. For part 2, there is no any specific instruction for that. You just need the data set that you've collected. You just need to submit the data set into the assignment port. Okay, for practical 2 plot. Okay, and for part 3, what you need to do is to start working on the data set. Okay, and you follow that instruction. Okay, that I've already attached, where you're going to state your topic, you're going to have a introduction, you're going to have a literature review, you're going to have analysis, and you're going to have a conclusion, and you're going to have a reference, and so on like that. So that is that. So did you get that? Okay. Uh, Thank you for that. So make sure you stay safe and do have a good day.